Week 7 interactive presentation. Okay, starting Week 7 interactive presentation involving using balloons to explain all the different electron domain geometries. Starting out with the first, I have the beryllium dichloride molecule. It has a total number of 2 electron domains. It is an AB2 molecule. The 2 outlining the fact that it has 2 electron domains, being that there are 2 bonds, the chlorine to the beryllium, that would indicate there are no lone pairs of electrons, and the geometry of this molecule, the geometry of the electron domain of this molecule is linear. Yeah, on to more. Okay, this next balloon model is to represent electron domains of 3, or ED3 molecules. I'm going to use it for a couple of examples, the first being boron trifluoride, or BF3. It's an AB3 molecule. As aforementioned, it has 3 electron domains. In this case, all 3 are bonded. The electron geometry is trigonal planar, and it is worth mentioning, because I'm going to use it for another example, it's worth mentioning that its molecular geometry is also trigonal planar. There are no free pair of electrons because all 3 are bonded. Or lone pairs, excuse me. The next example I was used for is sulfur dioxide. It is also an AB3 molecule. It also has 3 electron domains. It is also trigonal planar in electron domain geometry. However, the big difference is there's only 2 bonded pairs. There's 2 oxygen bonded to sulfur, and this guy right here would represent the lone pair of electrons. The reason this is significant, the reason I brought up the molecular geometry is this changes the molecular geometry of this molecule. Instead of the aforementioned trigonal planar, this would be a bent molecular geometry. That's a significant difference, but on to the next. All right, my next balloon model is going to represent AB4 molecules. I'm going to provide 3 examples of AB4 molecules. Everyone's going to have similarities as well as differences. All of them, because they're AB4 molecules, all of them have 4 electron domains. And all of them will have the same electron domain geometry of a tetrahedral. The first I'm going to begin with is methane, or CH4. Carbon has 4 valence electrons. Hydrogen needs 1. That's a pretty easy deal there. Carbon fills the octet rule. Hydrogen's happy. That creates 4 bonds and no lone pairs of electrons. As aforementioned, the tetrahedral electron domain geometry, as well as tetrahedral molecular geometry. And that's important because of the next couple of examples. We're going to use the same thing for ammonia, which is NH3. Nitrogen has 5 valence electrons. Hydrogen still only needs one, so that's going to leave two. So there's going to be one lone pair, which is going to alter the molecular structure to that of a trigonal pyramidal structure. Finally, water. Let's see, oxygen has 6 or 16, in this case it'd be 6. Hydrogen still just needs one, and there's only 2 hydrogen. So, actually I'm going to take a step, no, we're going to keep going, sorry. Hydrogen still only needs 1, so that's going to leave 4 leftover valence electrons, or 2 electron pairs. Once again, this alters the molecular geometry. In this case, it would be bent. I'll include diagrams of what I was going to say pertaining to the ammonia. Because just the shifting in the molecular structure it's important, and I want to give a visual. The big thing is, I mean, it essentially looks like this, molecular speaking as well, but what's not really accounted for, I mean, it is accounted for, where all the balloons are tied together, that is the central atom. When you look at models of molecular structure, there is that central atom, and then there's bonds off of that with whatever geometry it maintains. So I want to give visuals on that. Okay, on to AB5 molecules. AB5 molecules all have electron domains of 5. They all have this electron domain geometry of this trigonal bipyramidal, 3 on the bottom, 2 on the top. I got the weirdest shaped balloons ever. Finally got a normal one right here. First one. I'm going to give 4 examples of electron domain geometries. And obviously I'm giving more than one because differing molecular structures occur pending the bonds formed or not. First being phosphorus pentachloride, PCl5. Phosphorus has 5 valence electron, chlorine 7, so it takes one. It takes 1 to fill chlorine's octet, being that there's 5 chlorines, and phosphorus has 5. That does it. You got 5 domains, 5 bonds, 0 lone pairs. Both the molecular geometry and the electron domain geometry are exactly the same as both the trigonal bipyramidal. The next example I would use is sulfur tetrafluoride, which is SF4. SF4 molecules, let's see, would require 4 of the sulfurs, 6 valence electrons. To fill fluorine's octet, all right? Fluorine has 7 valence electrons, sulfur with 6. So 4 of those are going to be used filling fluorine's octet, and that is going to result in 2 lone pairs, my God, do math. It's 5 domains, 4 bonds, 1 lone pair. This is going to shift the molecular structure to that, or the molecular geometry to that of the seesaw shape. Next is chlorine trifluoride, which is ClF3, both with 7 valence electrons. Fluorine's octet are filled with 3 bonded pairs. However, 2 lone pairs remain. On a side note, this does kind of violate the octet rule for chlorine. Nevertheless, these 2 lone pairs change the molecular geometry even further to a T-shaped. Let's see. We have iodine difluoride, and this is actually an ion of iodine. It's I negative. It's IF2 negative for the compound, but the iodine is it's an ion of iodine, which is significant because that means there's an extra electron. The 2 fluorines bond with the iodine, which with the extra would have 8 electrons, and therefore 6 remaining. Those 6 remaining are going to form 3 lone pairs, and 3 lone pairs is going to alter the molecular geometry even more to a linear shape. I'm sure I tripped all over my tongue on that one, but one more to go. And last but not least, we have the AB6 molecules. My balloon model here, which is 4 on this plane, and then 2 going right through the middle there. AB6 molecules have 6 electron domains, and all AB6 molecules have the octahedral electron domain geometry. I'm going to give 4 examples. Same deal. Each one's going to have a regressing molecular geometry. First one would be sulfur hexafluoride, which is SF6. Sulfur's 6 valence electrons bond perfectly with fluorine 7, given that there's 6 fluorines in this in this molecule. The octets of the fluorine atoms are filled. There's 6 electron domains, 6 bonded pairs, no lone pairs, forming the octahedral electron domain geometry, as well as an octahedral molecular geometry. So moving on to bromine pentafluoride, BRF5, 7 valence electrons for fluorine, 7 for bromine. There are 5 fluorine atoms present, so 5 of those 7 valence electrons from bromine are going to be used. It's going to leave behind 1 lone pair. So there's 5 bonded pairs, 1 lone pair. The molecular geometry is going to shift to square pyramidal, but still the electron domain geometry remains the same as it does in the next one, which is xenotetrafluoride. And the last 2 both include xenon, and that's because xenon can have more than 8 valence electrons in the outer shell, which is fascinating to me. So xenon tetrafluoride, which is XeF4, xenon already has 8 valence electrons, fluorine with 7. 4 bonded pairs would be created. That leaves 2 lone electron pairs. There's 4 fluorines, each with 7 valence electrons. 4 of xenon's valence electrons are going to be left over, 2 pairs. And this ultimately is going to shift the molecular geometry to a square planar geometry. Finally, xenon difluoride, Now you have only two bonded pairs because there's only two fluorine atoms. And yeah, two bonded pairs is going to leave three lone pairs. And this is just going to shift the molecular geometry into a more regressive state of linear. And what I was talking about before, and it's we're just gonna wing it here. These balloon models represent electron domains. They don't represent an atom being there bonded. They represent the potential for it to be there. When it's not there, you're left with this lone pair of electrons, which essentially you just would take that out of the equation and you would have two electrons floating, which ultimately changes, and why it's significant is because it ultimately changes the molecular structure of things, because this is all push-pull. So when you have, six of something, but you take one out, but yet something is still there, it just allows everything to shift. It changes the angles of the bonds and changes the shape of the structure, essentially. But yeah, that's why you can see such a variance from this to just a linear molecular structure, is because this does not mean that these are all atoms. They're potential bonds. Right? Thank you. Week 7 interactive presentation.